So we're going to continue on in chapter 9, and we're going to work with graphing in chapter 9. So we've talked about those compositions, we talked about polynomials. Let's start looking at what these graphs actually look like. So a quadratic function results in this U-shaped graph, which we call a parabola. So it has a very specific name. When we have something with x squared and you start plugging into your table of values, negative 2 squared is 4, negative 1 squared is 1, and so on. So you get this nice curvature that's happening here. The lowest point or the highest point, if it's upside down, is called the vertex. And the line where you could fold the parabola perfectly in half is called the axis of symmetry. So these are some key areas where we want to name things with our parabolas. So the lowest point there would be the vertex. The vertical line that I just talked about is called the axis of symmetry. And a parabola is always symmetric about a line, always, because you get that pretty U shape. Any function can be written in what we call standard form. So we talked a little bit about this in the composition section. We want to write the x squared first, then the x, then the constant. That's considered that nice standard form. When the highest exponent is a 2, we call this a quadratic function, and it's going to have that nice U shape. So when we're graphing these parabolas, we can shift them around in the plane. I can move them up, down, left, or right. If I want to do x squared plus 3, that plus 3 is outside of the x term. So it's considered a vertical shift. If I want to go plus 3, I'm going to go up 3. So let's watch the proof of this. I make my table of values, so I'm plugging in my numbers, and I'm plotting my points. What do you notice? Instead of the vertex being here at 0, it's up here at 3. So I could have generated this just by taking that parabola and moving it up 3 units. Now, the lowest point is at 0, 3, and my axis of symmetry is the y-axis at x equals 0. My domain is all real numbers because it's a polynomial. And my range is going to be from 3 to infinity because this parabola doesn't exist before 3. There's nothing there. So if I go from the bottom to the top, it starts at 3 and it keeps going. So the graph of x squared plus any constant number is always going to be a parabola. It's always going to have the same shape. If I'm adding something, I'm going up. If I'm subtracting something, I'm going down. And my vertex would always be at 0, the number that you have added or subtracted. So what happens now with a horizontal shift? This time, that plus 2 is next to the x. So now, I'm going to make my table of values and let's see what happens. What did that do? It shifted it left 2. Did you think it was going to go left? No, probably not. You probably thought it was going to move to the right because we're adding. So the additional step here is that when you're dealing with a horizontal shift, it goes opposite of the way you would think. So if I'm adding, I'm really going left. If I'm subtracting, I'm really going right. So that changes my vertex. My vertex is at the x-axis, but it's at negative 2, 0. My axis of symmetry is no longer the y-axis. It's now this vertical line, which is at x equals negative 2. My domain is still all real numbers, and for my range, I go from the bottom to the top, and it starts here at 0, and it goes up forever, which would be 0 to infinity. So we can make a new rule here where we can say, well, if I subtract something inside the parentheses with the x, it's going to have that shift. It's still going to be a u, but it's going to shift left or right. And my vertex is going to be that value I've subtracted, 0. So let's look at what's happening with 2 shifts. So if I have minus 2, I'm moving it to the right 2. Then I have this plus 1 outside, which means I'm going to move it up 1. So let's make a table of values and just make sure we're on the right track. So I plot my values, and I connect my dots. And what you should notice is that we have that vertex was shifted to the right 2, like we said, and up 1. So my new vertex is at 2, 1. My new axis of symmetry is x equals 2, and my range is going to be from 1 to infinity. So here is a way of just formalizing that behavior we're seeing. Now I can see my vertex is going to be at h, comma, k, and then my vertical line would be at x equals h, the value that's being added or subtracted. So we're just trying to formalize those things we saw in that previous image. So now let's look at what happens if I put a number in front of x squared. How does that change things? So when I put a number in front of x squared, it affects the shape of the graph by making the parabola more narrow. The negative sign also makes my u flip upside down. It shifted 3 units down because I'm subtracting 3 outside those parentheses. So what does that look like? Let's make a table of values and double check what we just discussed. So I'm going to plot my points and look what happens. That u is upside down. It does look slightly more narrow, and my vertex is now a maximum. So because it's upside down, my vertex is now a maximum of 0, -3, and that's not going to change my domain. It's not going to change my axis of symmetry, but it is going to change my range. So now when I go from the bottom to the top, the graph exists everywhere until we get to this -3, then it stops existing. So we're going to have negative infinity to -3. That's a typo. That should be -3. So I'm taking this side and I'm formalizing this. If I get a wider value, that would be between 0 and 1. If the value in front is greater than 1, it's going to make that parabola more narrow. And that's going to be really hard to visually get. So it's a really good idea just to get a table of values when you're graphing these parabolas in the assignments and plot a few of those points to notice that behavior. So we have this 1/2 x minus 2 squared plus 1. I know I'm going to the right 2. I'm going up 1. And that 1/2 is going to affect my parabola. It opens up because 1/2 is positive. It's going to be wider because it's between 0 and 1. My vertex has been shifted from 0, 0, 2 to the right, up 1, which is that point 2, 1. The axis of symmetry is at that coordinate of the vertex, x equals 2. And I would plot my points from my table of values and connect the dots. The domain is always the same. The range would be from here, which is 1, all the way up to infinity. So let's look at how would I start describing these graphs with quadratic functions. Well, a lot of times we have data and we try to figure out, well, what's the best way to describe this data set? Is there any kind of mathematical reference point that we can have here? So if I look at 0 time, if I know that at 0, my data is at 5900, I would plug in 0 for x, and that way I know the constant value is going to be 5900. Using that table then, if I plug in 4 for x, I should get out 7300. So I know if I plug in 4, I get 7300. If I plug in 8, and then I'm going to simplify the equations. So the numbers I'm plugging in are becoming those coefficients. And then I can simplify the system of equations, eliminating a value, plugging it back into the original, and I get 525. So I created a system of equations out of that data. So I plugged in 4 and I plugged in 8 because I had the same values there. Simplified them out. Plugged in 4, plugged in 8. That's where the coefficients came from. Then I replaced C. I formed my system of equations. I subtracted. So I subtracted that 5900 over to both sides. Then I'm just going to eliminate B. So I'm going to multiply by -2 up its top and get 43.75. I plug it back in, and that's how I get my answer. Then I can go ahead and take my quadratic, and I know my A would be this value and my B would be this value. So this is how we go from a data set to an equation.